Good evening, everyone. My name is Andrew Fracknoy. I'm the Emeritus Chair of Astronomy here at Foothill College, and it's a real pleasure for me to welcome everyone here in the Smithwick Theater and everyone listening to us or viewing us on the web to this lecture in the 19th Annual Silicon Valley Astronomy Lecture Series. Tonight's program will be about Pluto's mysterious moon, Charon. Our speaker tonight is part of the team that's been exploring the world of Pluto with the New Horizons spacecraft, and I will introduce him more formally in a second, but let me just say that this series of programs is sponsored by 4 worthwhile organizations that we'll hope you'll get to know more about: the Foothill College Science, Math, and Engineering Division, the NASA Ames Research Center, one of the premier NASA centers in the country, the Astronomical Society of the Pacific, a venerable organization in public outreach, and the SETI, the Search for Extraterrestrial Intelligence Institute. And we're grateful to all of them for their sponsorship. Tonight's speaker is Dr. Ross Beyer, a planetary scientist with the Carl Sagan Center at the SETI Institute, and also at NASA's Ames Research Center. His interests include the surface features, the surface processes, remote sensing, and photography of the solid bodies in our solar system. As he likes to say, if you can stand on it, he's interested in what it's like and how it got that way. He was a participating scientist with the Lunar Reconnaissance Orbiter camera, serves as a co-investigator with the HiRISE instrument on the Mars Reconnaissance Orbiter, and has worked to help certify safe landing sites for Mars landers and rovers, starting with the Spirit and Opportunity rovers. He's also a member of the New Horizons science team that explored the Pluto system and is currently exploring the Kuiper belt of icy chunks beyond Neptune. He is going to speak tonight on Charon, Pluto's companion, what we're learning from New Horizons. It's a privilege for me to introduce to you Dr. Ross Beyer.
Thank you, Andy. Thank you. All right, well, thank you for coming out this evening in the rain, as they previously talked about. Tonight, I'm going to talk about a small icy world that orbits far from the sun. And in the summer of 2015, surprisingly, almost 4 years ago now, I can't believe that it's been that long, we flew through the Pluto system with the New Horizons spacecraft, the diagram that you see up there in the right. Now, a lot of times you'll see spacecraft shown this way as artist's conception as they fly through the solar system, but I often like to think about spacecraft as they are when they're real on the ground. And this is an example of the New Horizons spacecraft when it was at the Kennedy Space Center right before launch. These engineers are prepping it for launch. Its power system is being connected, and it's about ready to get put on the spacecraft. Right? It's about the size of a grand piano. And this is also an opportunity for me to tell you about how important people are to space exploration. As the PI of New Horizons, Alan Stern, often likes to say, space exploration is a team sport, and that is certainly true for New Horizons. Although I'm up here in the spotlight this evening talking to you about the science that we've done, a whole team of scientists have worked with me to come to these conclusions. And behind that team of scientists are the flight engineers and the others that have navigated us from the Earth to the Pluto system and beyond. And behind them are engineers like this that help launch the spacecraft, that help build the spacecraft, and to help all along the way. So what happened after the spacecraft left the Earth? Well, this is a brief map of where it went and how far it went. It launched in January 2006. It flew by Jupiter in 2007, through the Pluto system in 2015, and just this New Year's we flew by our first Kuiper belt object, MU-69. Now, our passage through the Pluto system was fast. We were on a rail riding that red line out of the solar system. And so Pluto and Charon and all of the moons of Pluto zipped by very quickly. And we tried to take photographs and measurements as we sped through the system. And of course, Pluto was certainly the star of the New Horizons show, and it did not disappoint, not by any means. In 2015, I had only been with the New Horizons team for about 6 years. And of course, others had been working on New Horizons before it even was New Horizons to get it made and built, had been involved with New Horizons for decades. And even they were overwhelmed with what we saw and what we learned. But tonight I'm not going to talk so much about Pluto, only the fact that it has this really interesting satellite called Charon that we're going to talk about tonight. But before I can really get into Charon, we kind of need to get some basis for how big Charon is, what it's like. So I present to you here a scale portrait of some objects that you should be pretty familiar with. You live on one of them. The other one we see in the night sky very frequently, the moon. And all of these are to scale, right? And so you can see Pluto and Charon over there in the bottom right. And Pluto is much smaller even than our own moon, all right, to give you an idea of how big these worlds are. Still very interesting in their own right. But an interesting thing about Pluto and Charon is the fact that they are a large kind of binary pair, not unlike the Earth and the Moon, but also different in many ways. So to get an idea of how they really are related to one another, I'm going to show you an image of these worlds scaled together. So now I've made Pluto and the Earth about the same size, and you can see how big Charon is compared to Pluto and how big the Moon is compared to the Earth. And you can tell that Charon is a lot bigger relative to Pluto than our Moon is to the Earth. Right? In fact, Charon's radius is 51% of the size of Pluto. Right? So it's big. It's almost half as big as Pluto itself. Whereas our moon is only about a quarter. It's 27%. Its radius is 27% the size of the Earth. The other thing about the two systems is how far apart the moon orbits from the Earth and how far apart Charon orbits from Pluto. In the very bottom, which you can probably just barely see, on the left I have the Earth and Pluto, and all the way over on the right, you can probably barely see it, is the moon. This is how far away the moon orbits from the Earth in distance, right? So the Earth's radius is going to be our measuring stick. The moon orbits 60 Earth radii away from the Earth. It's really far, right? It took the Apollo astronauts 3 days to fly there. Whereas Charon is only about 16.5 Pluto radii away from Pluto. So it orbits much closer and it's much bigger. And the interesting thing about all of these things is we often think about objects orbiting other objects in the solar system, right? The planets go around the sun. The moon goes around the Earth. But that's not really quite true. It's a very polite white lie that's often told just to get you seated, right? What really happens is when two objects are going around each other, they really orbit something called the common center of mass. Often astronomers will call it the Beyer center of a system. And this is not terribly different from the way that you might have two ice skaters, right? So here's an image, right? You have these two ice skaters, and they're holding hands, right? And they're spinning around, right? And they're not really going one around the other because the ice skaters are the same size, right? They're both adults, right? And so they're really kind of going around or orbiting this central part, maybe where their two hands meet in the middle. But if they're not both adults, if one of the ice skaters is an adult and the other one is a child, right, then the center of mass, right, the place where they kind of go around is closer to the larger object, right? And in this case, maybe inside that larger object, right? And you can see that if you go to the ice skating rink, right, little kids are whipping around and the adult is kind of in the middle. But if you have two adults right there, they'll be co-orbiting. And so this is true, of course, in our solar system, in our Earth-Moon system, and in the Pluto-Charon system. In fact, this diagram is, of course, not a diagram of ice skaters. This is actually a diagram of the Earth and the Moon. Because the common barycenter of the Earth-Moon system is about 75% of the radius of the Earth away from the center of the Earth. The Earth actually does this wobble with the Moon when the Moon orbits every month. You don't notice it, because the Earth has so much gravity, we don't notice it. You have to be able to do a lot of precise measurements to even detect that. And so when we take this concept and we go out to Pluto, since Charon is so much bigger, it actually drags that barycenter out from outside the surface of Pluto, and Pluto and Charon kind of co-orbit this spot in space. This is a diagram made by one of my colleagues at the SETI Institute, Mark Showalter, and it shows the other satellites of Pluto spinning around. And the thing that you may notice is that Mark has put little white dots on one side of each object so you can see, kind of keep track of what's spinning where. And as you know, the moon, when you look up into the night sky, the moon always looks the same, because the same face of the moon always faces the Earth. It's called being tidally locked, right? So everywhere on the Earth looks up and they always see the same side of the moon, right? But if you were to stand on the moon and look back at the Earth, of course, the Earth is spinning underneath the moon. And so you could see different parts of the Earth from the moon. And that's why everybody around the Earth knows that there's a moon, because they can see it from no matter where they are on the Earth. But if you were on Pluto and you looked up at Charon, you would always see the same face of Charon. Okay, great. It's just like here on the Earth. But if you lived on Charon and you looked down at Pluto, you would always see the same face of Pluto. And more importantly, if you lived on Pluto at the white dot, Charon would always be in the sky. Always. It would wane and wax, but it would always be in the same spot in the sky. And if you happened to grow up and live on the other side of Pluto from the white dot, and you grew up and you got a job and you moved around to White Dot City, suddenly you'd be like, whoa, there's a moon! Because you would never see a moon on the other side of Pluto. You just wouldn't. All right, so that's an interesting entree into Pluto's dynamics, but none of that actually matters to the geology, which is what I'm really here to talk about. But the other thing I need to divert into is about how I'm pronouncing the name of this moon. Right? I pronounce it Charon. And those of you with a classical education, or those of you that are in fact Greek, will roll your eyes and say, oh, that's not how you pronounce that. Because what you think of when you see this word is you think of this guy, the boatman of the dead in classical Greek mythology. And so, since you know that that word is associated with classical Greek mythology, and you know that other words that we have in English that come from Greek, like chaos, start with a hard CH, right, chaos, you would assume quite correctly, that this word also starts with a hard K, and it would be pronounced Charon. But that's only because you know perhaps part of the story. The other part of the story comes from the fact that when human beings discover new objects in the solar system, they have a wide latitude of how to name their new object. Now, there are rules, of course. The larger the object, the more rules there are, one can say. So when Charon was discovered by this guy, this is Jim Christie in 1978. And in 1978, astronomers looked at photographic plates because they didn't have computers so much. This is Jim in 1978. And Jim was taking observations of Pluto from the Naval Observatory. Of course, Charon on the right, as we know it today. On the left here is a picture of Pluto and Charon. Right? So astronomers, of course, they look at photonegatives. They don't bother generally to develop the plates, so stars are dark instead of bright, but you can get over that. What Jim noticed is that if Pluto was a planet, of course, which everyone knew by 1978, it should just be a bright dot in his telescope, right? But what Jim noticed is that there was a bump on Pluto. And a lot of other people had seen this, and they thought, oh, maybe there's just something funny about the plate that night or something. But Jim took a lot of observations, and Jim noticed that the bump kind of moved around Pluto like a clock. And what we know today is that Pluto system that we were just looking at, right, Pluto's system is tilted relative to the plane of the solar system. And so when we look at Pluto, we see the moons going around, just like we saw in that image that I showed you before. And so what's happening is that bump is Charon going around Pluto. And that's what Jim detected in his photographic plate. All right? And so Jim found a new moon, right? This is a big deal. 1978. And so Jim had the ability, it wasn't just Jim, he also worked with a gentleman named Robert Harrington, who's also co-credited with the discovery. But Jim, of course, was married. This is a dark picture, sorry, it didn't work out so well. It's an old photo. So Jim, of course, was married. His wife's name was Charlene. But Charlene was too long. No one called her Charlene. Everyone called her Char, right? And Jim thought, wow, I'd really love to name this after my wife. But Jim also loved science, right? He was an astronomer. He loved physics, and he loved protons and electrons, and he thought that words that ended with O-N were really good words, right? They were good science-y words, right? And so Jim thought, I'd really like to call it Charon, after my wife and after science, right? And so, Jim loved his wife, Jim loved science, but he didn't maybe know Greek mythology so well, and so we can only imagine his delight when he learned that this word was a great word to use to name something that was orbiting something named Pluto, right? So that's why many astronomers, and you heard Andy pronounce it this way too, pronounce it Charon, because that's how Jim pronounced it, because he named it after his wife. And there they are today. Still alive, still doing great in Flagstaff. All right, so a lot of times people ask me what I do for a living, and I tell them that I'm a planetary scientist. And that usually is not super helpful for people, right? I'm a scientist that doesn't really give them an idea of what I do. So sometimes I tell them that I'm like a geologist for other planets. And they're like, okay, that also necessarily doesn't help them because they maybe don't know what a geologist does. They know it has something to do with rocks, right? And so on good days, on my best days, I'm like Ansel Adams in the solar system, right? My computer screens are full of beautiful photographs and data from planets in our solar system. Right? On bad days, my computer screens are full of spreadsheets and documents and reports, just like anybody else's bad days. But even planetary geologists and geologists for other planets may not be super helpful to people. And so really what I am is a crime scene investigator, right? I have photos and data, and I have to find out what happened, right? Just like a detective or a crime scene investigator, they show up, and there are clues, and they try and figure out what happened, right? And so before I can really bring you along on this journey of how we figured out what's going on Charon, I have to train you a little bit, right? So we're going to work through some planetary crime scene investigations just to kind of get you warmed up, all right? So here's our first crime scene. It's the Earth. This should be easy, right? It's the Earth. We have here some trees in the foreground surrounded by, I'll even give it to you, a plain of basalt. All right, what happened here? Ah, very good. But when? What came first, the trees or the lava? The trees, very good. So the sharp-eyed among you may notice the smoke plumes in the background or even some of the cherry red spots in the foreground, although this isn't a great photograph. And so this lava is fresh, right? So certainly the trees came first, the lava came after. But one might wonder, lava versus trees, lava is pretty much going to win. Why do we still have trees in this spot? And the answer to that question is because the trees are on a little hill. And so the lava flowed around and left the trees, and the lava is around them. Okay, great. Good first start. I'm liking it. You're doing great. Let's try another one, a little harder. This is a photograph of Canyonlands National Park in Utah. Lovely place. I highly recommend going there. But what you'll see here is a sandstone area here. You see this very regular grid of cracks and joints, as geologists like to say. And you see these big lanes between the sandstones, these very straight, very empty lanes, as if someone took a giant rock clipper and just shaved off a couple of rows and then left, right? Why are they like this? What happened here? Water. Haha, well, no, some of that. So let me tell you. So what happened here is that the rocks that make up the sandstone that you can see, the high stuff, actually slid apart, like they were on a conveyor belt. And you'll say, why? How? Well, he's the geologist. Certainly he must know. Well, let me tell you. So you need a little more information than this photograph can give you. So what I'm going to do is I'm going to tell you a short story about this area. So once upon a time, there was a big rocky basin here. And there was a big sea that occurred in the basin. Sea dried out, it left a salty layer, a layer of salt, right? And then sand came in later, blew in, lithified, and became sandstone. So what you've got is you've got a basin of rock, you've got a layer of salt, and you've got a layer of sandstone. Now the interesting thing about salt as a geologic material, as opposed to salt as a condiment, is that salt as a geologic material is plastic, it flows. So if you push on it with a heavy weight, it'll kind of deform, right? But since it was in this bowl, the heavy weight of the sandstone above it really didn't do anything. It just stayed there. Until the Colorado River up here cut through the basin. It cut through the sandstone, it cut through the basin, and it cut through the salt layer. And when it did that, the salt layer had somewhere to go. And so the weight of the sandstone pushed the salt, and basically the sandstone rode on top of the salt layer like a conveyor belt and opened up these lanes in the sandstone. Okay, good. Hopefully you're getting an idea of where we're going. Let's try an extraterrestrial example. Not super extraterrestrial. This is our moon, okay? On the left, many craters. On the right, not so many craters. What happened here? Well, the answer here is that craters in the solar system, as Kevin Hand, who was here last month talking to you, said, craters in the solar system are like footprints in the snow. In places where you see a lot of footprints, that snow is probably pretty old. In places where you see fresh snow and not many footprints, that's probably a pretty fresh deposit of snow. And what happened here is exactly that. This area on the left is older. The area on the right is fresher because a lava flow on the moon, a long time ago, flowed out and covered the right-hand side of this frame, right? And so in reality, there are just as many craters on the left as there are on the right. It's just that on the right, they're covered up by a layer of lava, all right? Now let's go to Mars. Don't worry, I'm not going to go through the whole solar system, although I could, but that'd be a different talk. Here's Mars. This is a very close-up view of Mars. And what you're seeing here, these little black dots that you might be able to see, are boulders, right? As big as a car, as big as a house. And they have these trails behind them. What happened here? Well, what happened here is that these are actually on a hill. It's high at the top of this frame and low at the bottom of the frame. And you know, there could have been seismic activity from a Marsquake, a nearby impact, or even just where the rocks were, they finally eroded and these big boulders fell. And so these tracks are the tracks that the boulders left in the dust as the rocks rolled downhill. And in fact, this one on the right is like my favorite because it starts up here. You probably can't see it very well. There's a track, and it's bouncing. It's like a dotted line, right? That means that this rock, as big as a car, is moving so fast that it is literally bouncing off the ground. And it bounces, and it bounces, and it bounces until it hits this crater. And on the right-hand upper side of the crater, it jumps the crater and lands on the other side, right? There's no track across the crater, but there's a track on either side. It bounces a few more times until it comes to rest down here, right? And so these are all examples of how looking at a photograph can give you an idea of what happened and help you solve the mystery of how it happened and what happened there in the past. Okay, let's talk about Charon. What happened here? Well, if you read my papers or maybe even read the abstract, you might know, but let's pretend like you didn't. And you can't really tell from just a single image, right? So let me walk you through the crime scene, so to speak. I'm going to show you the data, and then I'm going to talk about the conclusions that we've drawn about Charon and why it's so interesting as a little moon. So a lot of the data that we can take as we fly by allows us to get images from multiple perspectives and allow us to recreate the topography of places that we see. And that's what this image is. This is where the bright yellows are high standing topography and the blues are low standing topography. And for those of you that can't see the legend, the span of topography on Charon is 10 kilometers. That's a lot for such a small object. So there's a lot of ups and downs on Charon, and you can see, I hope, that there's a lot of variation. There's this kind of belt that runs across the middle of Charon. There's my dot. This belt that runs across the middle of Charon. And north of there, there are these big kind of chunks and canyons. And south of there, the geology is very different. If we zoom in on an area there north of the canyons and adjust our color scale a little bit to give you a better feel for what we're seeing, you can see that the crust here, right, we're looking at a whole planet, so we're looking at big chunks of the crust here. There are blue lanes in between these big chunks of Charon's crust. Now, just like the example that I showed you in Canyonlands, where things slide apart and leave a trench in between them, we think that's what's happening here. But this is happening at a much larger scale. And more importantly, if you know anything about Earth tectonics, right, plate tectonics, you know that in some places on the Earth, the plates are spreading apart, right? And we're creating new crust, for example, in the Atlantic Ocean. But in places nearby us, like around the Pacific, the plates are coming together, right? And so if you have plates, if you have plate tectonics on a spherical planet, in some places the plates are coming apart, and in other places they're coming together, right? It's just a conservation of area on a sphere. But what we find on Charon is that everywhere these chunks are coming apart. And that just, right, it doesn't make any sense from what I just told you, right? If it's plate tectonics, they got to come together somewhere, otherwise something's funny. And the thing that's funny is that plate tectonics are not happening on Charon. Instead, what's happening is that Charon got bigger, all right? So what I want you to think about is blowing up a balloon, right? Blow up a balloon, and then I want you to take maybe some house paint, like some good latex paint, and paint the outside of the balloon, right? Let it dry, maybe overnight. And now I want you to blow into the balloon a little bit more. And when you do that, the balloon gets bigger, and the paint is going to crack. And these little plates of the paint are all going to get separated from one another. None of them are going to come together because the whole balloon is getting bigger. And that is what we think happened on Charon, but I'll get back to that. And so, since Charon got bigger, you have all of these tectonic movements of the large chunks of its crust. And it gave rise to these beautiful canyons that we see, and also these scarps, right? They're canyons and cracks of all kind on the northern parts of Charon, and really all over. And so that's part of Charon's story, these big cracks in the north part of the planet. But in the south part, it's different. There's still some small cracks, but the character of the surface is very different. I'm going to call them smooth plains a lot, because that's a geology term that I use. Of course, if you look, you're like, they're craters and they're all kinds of things. That's not smooth. For me, it's smooth in comparison to the north. And if we zoom in on parts of this smooth plain, these smooth plains, of course, they aren't completely smooth. We see places where there are small cracks that are lined up next to one another. But also, there's just this general smoothness at the highest resolution that we can find on Charon from our flyby, and this is what that is. There are places where, as in the upper left, the surface is smooth. There are places in the photograph in the lower right where the surface is a little more pockmarked at a very small scale. And so that's fascinating. The story that we come up with to explain the crime scene has to incorporate all of these elements, right? The other thing about these plains on Charon is that there are some mountains that just randomly stick up out of the smooth plains. There are three big groupings that are labeled here. And this is a good point for me to mention that there are some names on Charon that are now official, IAU names. There are some names that are still unofficial. And you can play the home game to figure out which ones are and aren't, if you like. But so we've named these mountains after science fiction authors, right? And artists. So Kubrick Mons, Clark Montes, and Butler Mons. And Kubrick Mons is really our poster child. Here's a better view of it. The upper left image shows you what it looks like from the spacecraft, just without any alterations, right? What it looked like as we flew over it. The bottom image is map projected, so you can see what it might look like if you were looking straight down on it. And as I said, we have topographic information across this part of Charon, and so the two profiles to the right give you an idea of what it would look like in profile. And as you can see, it's kind of a sharp mountain. You can see peaks on it, and it just kind of sits almost randomly in this smooth plain. And the other thing that you might notice about this mountain that's different from other mountains you may know is that it seems to have a moat around it, right? It's like a mountain in a moat. How did that happen? Well, I'll tell you, I think, that what happened is that the material that formed the plain came around afterwards and surrounded the mountain. The mountain was there before, just like the trees in our earlier example. The other mountain, the biggest mountain, is Butler Mons, and this is an example of some of the maddening parts of being a planetary scientist. These are all of the photographs of Butler Mons that humanity has. The white arrow points to the peak of Butler Mons in all cases, and is an example of when we're farther away, right? So remember, we're like an arrow shot through the bullseye of the Pluto system, and when we're farther away, the images are fuzzier. As we get closer, right, to the bottom of the sequence, the images get crisper. But the other thing that happens, of course, is that Charon rotates. And so you can see that Butler-Mons is in sunlight in image A, and as Charon rotates, it rotates into darkness. And so at our best resolution, when we could have seen it the best, the sun has set on Butler-Mons, but its peak, there's one little white pixel that you can probably barely see from the audience, but there is one bright spot where the sun is still shining on the very tip-top peak of Butler-Mons, but its lower flanks are in darkness. And so that's a pretty cool thing. In other places on these smooth plains are these features, not the craters, not the sharp little cracks, but these other things that look like puckers in the surface. Now, when I write science papers, I can't use pucker. It's not a good science word. And so I have to say things like convex swells and depressions, right? But these are weird, right? I mean, I'm a geologist, and I looked at planetary images, and these are weird, right? These are hard to explain. What kind of process would have left features that look like this? So I have a guess. We call it a hypothesis in science. Dresses it up a little bit. What we think happened here, much like I told you that I think the surface that flowed around those mountains, it flowed around the mountains, and that's what emplaced the smooth surface. And here, what we think these are drains where the smooth surface kind of drained back into a vent that it might have come out of, right? So you can imagine maybe you're making like a yogurt or a chocolate, right? And if you poured it right into a crack, right, you would see these kind of waves as the fluid, the thick fluid, like went down into the crack. And if you flash froze it, you might see something that looks like this. Or something completely different may be happening here, but that's our guess, right? So this next is an image, is a movie of a flyby over the terrain of Charon to kind of give you one more view of the data. Here we are flying west over that big canyon. You see the smooth plains to the right and the more chunky, blocky northern terrain on the left. Here, as we come over the canyon, we take a bit of a turn to the north, and you can look back over the canyon that we just flew over. As we come up toward the North Pole, we see this big crater, Dorothy Gale crater, and the dark polar area. And you can see as you look at the limb that there are just these big chunks and big depressions of the crust as they were pulled apart and then, of course, filled in afterwards. But it's very chunky, right, as these blocks were. And as we come across that boundary, these southern plains have a very different morphological character. They look very different. So any story that we come up with, as I said, has to be able to account for all of these clues, right? So what kind of a story can we tell that is consistent with all of these data? To do that, we need to talk a little bit about how planets are formed, okay? So, in the beginning, let me fast forward a bit. Once we get to a spot in solar system evolution where you're starting to form a planet, right? This is the sequence of kind of how it goes, a rocky planet, right? So in the beginning, you got some rocks, and they start glomming together, right? They hit into each other, they start to build a bigger pile of rocks. Eventually, there's enough of the rocks together that they start to get hot, and that's what the red coloring in the center of the second image on the left is trying to tell you. So the interesting thing about planets, from a geologic perspective, is that they are basically little heat engines. Interesting geology happens when planets get hot, okay? So what happens, how do you get this rock to heat up, right? Because, I mean, it's just rock. How does it get hot? Well, first off, when planets form and all of those impacts come together, there's some heat from those impacts, right? Everything you need to do to go from a small rock to a planet is about impacts. That's what gets all the mass in. And those impacts are going to heat things up a little bit. We call that heat of accretion. But the other thing that happens is when you build a rocky planet, you have a wide spectrum of elements that make up the rocks. And some of those elements are, of course, radioactive elements. And so, not very many, but if you get enough rock, you're going to have some radioactive elements. And certainly early in the solar system, those elements still have a lot of half-lives left. And so they're going to decay and give off heat, right? And so that, primarily, is what gets the heat engine starting. There are other kinds of chemical reactions that happen in the deep cores of planets that also perpetuate that, but that's the basic story. And eventually you get things hot enough where differentiation of a planet happens. And what that means is basically you get hot enough so that the light stuff rises and the heavy stuff sinks, right? And that's what leads to planets like our own Earth that have a molten iron core or a heavy iron core, right, and the lighter elements float to the top. That's how planets form, right? Okay, so what happens when there's a lot of ice involved with your rock? What happens then? So this is what's going to happen for Charon, right? We have a ball of ice and rock that's gotten together. How does that differentiation story play out when you've got a lot of ice? Well, this is what happens, right? You start with a kind of even ball of rocky ice, and because of that heating process that we talked about, it gets warmer. And what happens when you heat up rock and ice? Well, the ice melts, and the water floats, and the rocks sink. But of course, if the water floats, it's going to encounter the harsh coldness of space, and so it's going to crust over, right? And so this image in the middle shows you a denser core, maybe an icy and rocky mixture above that, and then this layer of water, a global ocean around the object that's covered by an icy crust. Now, over time, a small planet like Charon is going to cool off, right? And as it cools off, that icy ocean, or that watery layer, that ocean layer, is going to freeze solid. And you're going to get left with something that looks like on the right. Now, these layers are not to scale, and there are people that spend lots of time trying to figure out the deep nuances of this heat budget of how planets form. But this is schematic, right? And you have just solid ice all the way down. Now, this is slightly different from what we might expect around giant planets, like Kevin Hand talked to you about last month. He talked about ocean worlds like Europa and Enceladus and Titan and Triton. And those worlds have the benefit of orbiting a giant planet. And when they go around Jupiter, they have tidal forces, and the tidal forces between Jupiter and these small icy worlds around them flex the ice shell. And that flexing produces heat. And so the heat curve for those doesn't peak and then decrease, it goes up. And so you can imagine that instead of freezing, if you go from the middle image here and heat it up some more, you're going to melt all of the ice down in the bottom. And you're going to end up with 3 layers, but you're going to keep that ocean layer because it's still hot. And that ocean layer is going to have a roof of ice and a floor of rock. And that's what we think is happening in Europa and other icy moons that orbit the giant planets. And this is the interesting thing about Charon. Before we went by Pluto and Charon, the only icy worlds that we had really good information about were these ones that orbited giant planets. And we knew they had these oceans. But we didn't know whether oceans were magical from being close to giant planets, right? That you needed a giant planet to flex you, to get you warm enough to have an ocean, or if it was possible to be, through the normal evolution of an icy satellite away from a giant planet, whether you could get an ocean. And Charon, we think, is evidence that shows us that that's just a normal part. If you're big enough, you have enough heat, you can melt that ice and you can get a global ocean. Now, it won't stay, because Charon doesn't have anything keeping it warm. It's going to cool off and freeze, right? So this is actually the core of the story that's going to help us solve the mystery of the images of Charon that we looked at. But to get there, we need to talk about ice. Now, you're very familiar with ice. Maybe not because you live in California, but you've been to icy places. You know about them. You certainly have experience with ice in your drinks. And the interesting thing about ice as a geological material, not as a beverage, but also as a beverage, to be quite honest, is that when ice gets, I shouldn't say ice. I should stop saying ice and water because those things mean very specific things to you. I should say H2O. When H2O is a liquid, right, the liquid molecules flow around each other, right? But when H2O freezes, it gets bigger, right? It makes these crystal lattices, right, that give us snowflakes, right? And it gets bigger. And when the lattice takes up more space, that H2O becomes less dense. And that's why ice floats, right? This is not a surprise. You all know this. Ice floats. But this is different from other kinds of materials. Usually, when you go from a liquid to a solid and you cool down, you get more dense and you get colder and you sink, right? Most things get more dense when they freeze, not less dense. But it turns out that that's actually a very useful property for ice and for our data. Because the other thing that happens besides just the floating, which is of course delightful, is that if you put water in a container and then freeze it, if the container isn't very strong, it's going to break, right? This is what happens when you freeze water in a bottle. And we think that this very same thing is what happened on Charon, right? It had this global ocean, and it ran out of heat, and it froze. And when it froze, that water got bigger. And because of that, it cracked the outer shell. Just like that balloon I was talking about earlier, it got a little bigger, and it cracked everything. And that's what has driven apart the pieces of the crust that we can see on Charon, all right? So the answer is global oceans freeze and cause blocks to spread apart. It causes an expansion of the whole planet. Not a lot, but just a little bit, enough for us to see and certainly make beautiful canyons like this. Whew, good. Mystery solved. Oh, right, the plains in the south. Okay, so let's talk about the southern plains. So before I hinted to you that a lot of the features that we see on these plains look like volcanic features, flows, right? And in fact, other places in the solar system that we know are icy, like Charon, also exhibit these features. They look, for all the world, like volcanic flows, but we know that they're made of ice, right? And so you might say, okay, great, you're the geologist, super, right? We know that on the Earth, when we have rocky volcanic stuff, that we have tectonics, we often have associated volcanism. Maybe we have the same thing in an icy situation. You have frozen lava, or cryovolcanism, as we say in planetary sciences. That's got to hang together, right? Well, there's a bit of a problem. You see, ice, as I talked about, when it freezes, it floats, right? Remember I mentioned that? And so if you had a crack in the crust that opened up, and there was, water or cryomagma, maybe it's crystallized a little bit, it's a little thicker, and it opened up, right? It's denser down there. It's not going to come up, it's just going to sit down there and freeze. And so there's really no way to make these features that look like lava features. This gives planetary scientists that study icy surfaces much angst. Oh, we don't get it. And trust me, we know the difference between glaciers and lava flows. They're different. That's not what we're talking about. These things have features that look for all the world like they were emplaced in a manner similar to the way that lava is emplaced. So how do we solve this mystery, right? Because if it's just ice, then ice isn't the answer, right? And it messes us up. But the answer is other stuff. So it's not pure ice, right? It's not like there's a filter up there that's making it pure, crystalline, perfect ice. There's other stuff in the ice. Not a lot of other stuff, but some other stuff. And so there's a story about some interesting water-ice chemistry that's going to help us close the books on this particular case, right? And the other stuff that I'm going to talk about is NH3, good old ammonia. Because the interesting thing about NH3, or ammonia, is that when it's mixed with water, it changes some of the chemical properties. If you have enough NH3 in your water, it changes that density relationship and allows the mixture to be less dense or close to the density of ice. That's good, right? All right, awesome. How much ammonia do we need in our ocean to do that, to change the density relationship, right? You need about 30% ammonia. All right, so that's a lot of ammonia. It's like a lot, right? So we have estimates for how much ammonia and other elements are in the solar nebula from where Pluto and Charon were born. And the percentage of ammonia is about 1% relative to the amount of water. So we need to go from 1% to 30 to get even close to being able to use that as an answer. The other problem, of course, is that if you had that much ammonia in your water, you wouldn't get the relationship that cracks the surface, right? Because then the density is all backwards. It's regular again, right? You wouldn't get the cracking. So the answer is in something called fractional crystallization. So those of you that don't know what fractional crystallization is, it's fine. I really don't expect you to. What happens when you have a mixture of ice and water, or of water, and NH3, ammonia, is that water freezes first. This is very important. So let's assume we have this mixture. You can see the ice lattice at the bottom, and you can see the ice lattice at the top, and you have this fluid that has water molecules, mostly water molecules, and there's one NH3 atom for every 99 water molecules. Not very many. But as the temperature goes down, the water molecules are going to form water ice crystals and float to the top, right? So it's just like as if you had a big bin of Lego bricks. Some were red and some were blue, right? You had one blue brick for 99 red bricks. And you went into your bin and you just started making stuff out of the red bricks. At some point, the ratio of the red bricks to the blue bricks is going to change if you're only making stuff out of the red bricks. And that's what happens in fractional crystallization. Those ice crystals, the water molecules, get together, and they don't get together with the NH3. They float away. And so what happens as you slowly cool this ocean is you're slowly enriching it, right? The relative percentage of ammonia to water changes. And at some point, you get to a level up to that almost 30% where the density relationship changes. And now the liquid is buoyant or very close to being buoyant and will allow you to rise up and perhaps erupt. And that is what we think happened on Charon. This is a schematic diagram by my friend James Keane, who's a co-author on a lot of the papers. James is a big fan of whimsy, and so the orca in the bottom right is A, not to scale, and B, not really appropriate. But I think it was mostly James's way of reminding me that that part is liquid, and the upper parts are icy. And so this is a cutaway of Charon. You can see the highly tectonized, right, those blocky, chunky parts to the left, and the smooth plains to the right. And so what we think happened is Charon cooled, as that ocean cooled, it started expanding, and it started cracking the crust, right? And that's what gives rise to a lot of these cracks that you're seeing from the side. But in the final stages of that ocean getting to the point where it almost freezes, the ocean that's left over starts to get a lot of ammonia in it that allows that ammonia-water mixture to rise up above the ice and spill out into this area over here and create these plains, right? The other great thing about ammonia-water slurry, right? It's not going to be liquid. It's probably going to be like a thick mush of crystals and fluid, right? Just like a lava is that in the very cold outer darkness of where Charon lives, it's super cold. And pure ice would freeze real fast. But ammonia and water, right, just like antifreeze, allows that material to stay liquid longer and to create the landforms that look an awful lot like lava. And that is what we think we see on Charon. This material rose up and it surrounded pre-existing mountains or high points. It flooded in the low places and left us this signature that we see on Charon. And that is the answer to why Charon is so different in these two different places. These are the clues that allowed us to create the story that is consistent, I hope you believe the story I just told you, that accounts, we think, for all the clues and arrives at a world that looks like this, orbiting Pluto so far from the sun. Thank you very much.
I'm just curious why Charon and Pluto are always facing each other, and why these other satellites why they're spinning and why none of them is facing the Pluto?
That's a great question. Let me bring that slide back up so that it can spin behind me. So this is actually a consequence of planetary formation. It has to do with tides that act between the two objects. Right, just like our moon is locked, it only faces the Earth. It has to do with the tidal bulges and material on the two objects. Eventually, all objects, given enough, right, like if you run the solar system like a clock all the way to the end of time, everything would end up being locked together like Pluto and Charon are. And this is a consequence of tidal evolution. And so the moon is locked to the Earth, but the Earth still has lots of other stuff happening and the liquid ocean on our surface that kind of allows it to keep moving around. Lots of other satellites in the outer solar system are also tidally locked to, right, they always face Jupiter or always face Saturn, and that's what's happened here. These little guys in the outer ring aren't tidally locked yet, but they're often in resonances. They spin around an integer number of times as they go around.
Thank you.
Yes?
I was hoping to get a little clarification about how the pucker marks form. So I think at one point in your talk, you said that the pucker marks form when something flows up and then it goes back into a hole, right?
Oh, yeah.
So are those holes still the areas where Charon was being, expanded apart and it just made a lot of little like pinprick holes, or is that something else?
Yeah, so we think that the cryoflows that spilled out over this area are a lot like lunar Mars. So there are a lot of different kinds of volcanism, right? You may be thinking of the classic kind of volcano. There's one volcano and you have a big flood of lava. We don't think that's what happened. We think that in this area, all across this, the southern part of Charon, let me get up because I need a visual marker. All across the southern smooth part of Charon, the crust was broken up and this cryolava came up in lots of places, just like the lunar Maria, and kind of filled it over. So there's not like one big volcano that we can find. It's kind of everywhere. And so we think those pucker marks are places where there's maybe a bit of a bigger vent. And so when lava on the Earth, in lava situations, in silicate and basaltic lava comes up, right, and it spills out, and sometimes at the waning stages of the flood, after the majority of the energy is spent on a volcano, sometimes the remaining lava close to the vent will drain back into the vent. And so we think that is a good analogy for what these things might be.
Thank you.
Yes?
These geologic processes you were talking about with Charon, are they unique to Charon, or do you see the same kind of processes occurring on other icy moons, such as those around Saturn and maybe even the Jovian moons?
It's a great question. So certainly other icy worlds in the solar system have tectonic patterns, this telltale sign of expansion. Moon Ariel, there are big grooves on Ganymede. There are lots of other places in the solar system where we see this example of expansion, where everything got just a little bit bigger. We also, as I mentioned, we see other places. So the tectonic story is seen in other places, but when objects are big to giant planets, there's a lot of other stuff going on as well. And so sometimes it's hard to extract the variables. One of the nice things about Charon is it just kind of did its thing and wasn't impacted by a giant planet that it was going around. And the smooth surfaces, as I said, there are other places in the solar system where we see kind of smooth icy material in lows or in other places, nowhere as big, as much area as on Charon. So this really helped us put that piece of the puzzle together for how these things are happening.
Thank you.
Hi, you mentioned or implied that New Horizons had to go pretty fast to get all the way to the Pluto system, and therefore zip by it pretty quickly. And so you have a limited amount of data. You've got some high res and you've got some low res pictures. Some of the geologic features ended up in the shadow.
Yep.
So the question is, how much more analysis can you get out of that data? Have you investigated 90% of it, or 8% of it, or there you go.
Sure, that's a fine question. So all of the data from our Pluto flyby is on the ground, of course. And so that's a hard question to ask a scientist. It's like, what's your favorite child? So, as a science optimist, you could certainly say, well, there's always more that you can do with the data. There are always new ways to analyze the data, to think about the data, to process the data. But science often happens in, there's kind of a large hump and then kind of a long tail, I often think. Certainly for flyby missions where we get data and then it's done. It's very different for orbital missions. But for Pluto, right, there were some big things like, oh, here's this for the first time. That's crazy. Let's try and figure out what happened. And there's a hump. There's like the initial press releases where it's essentially, wow, that's crazy. Here's our first guesses at why we think it's like that. And then after some time, the first like real science papers come out where we've done the analysis of the data. And then there's a really long tail, and that tail can be very long, right? I mean, there are still people analyzing data and finding new science in Voyager data and in Galileo data. And so, these data sets are treasure troves that can be used by future scientists to learn new things that we haven't even thought to ask of them yet. Yeah.
Yeah, so this question is more sci-fi than anything. Is there a chance that Charon would be colonized by any means in the future?
Maybe. So Charon is like really far away, right? So is Pluto. They're hard to get to, and they're super cold. So you need to have a good reason to go and stay there. And I don't know what that might be. It'd be an awesome place to vacation. It'd be super cool to go to. But whether it has, you'd have to bring a lot with you, right? You wouldn't be able to live off the land maybe so much. But, I mean, there is ice there and there's water, so you'd be able to use that to create oxygen to breathe and water to drink, and maybe rocket fuel to get you off. So it's not terrible, but it's a really long ways away, right? So we launched in 2006. We got to Pluto in 2015, and we were going so fast we couldn't stop. So it's a long trip.
So in that case, you could build a second spacecraft to go and explore Charon once more and get more information.
I love it. Yes, absolutely. That'd be great. Because certainly there are parts of Charon that we haven't seen. As I said, the system is tilted toward the sun, so we really mostly just saw the northern hemisphere of Charon. The southern poles of both Charon and Pluto were in darkness during our flyby because they were facing away from the sun. Thank you.
I would think that methane would show up, frozen methane in your slurry and stuff like that. Did you consider that?
Yeah, so we see there's a lot of methane chemistry on Pluto right now. Certainly methane would be a constituent component of the ice, right? It would be part of that other stuff that I talked about. Methane doesn't have a big bearing on the chemistry and the rheology of the flow, so I really didn't talk about it much. Today on Charon, we don't see a lot of methane. Charon is small enough that any methane on its surface would mostly kind of escape today, but certainly there had to have been some when it was formed. Yeah.
I'm curious about the difference in gravitational lock between Earth and our moon versus Pluto and Charon, in that Pluto and Charon are locked with each other, always facing the same way, whereas with Earth it's merely one way. Right. Is that a function of the difference in masses or of the distance, or is Charon generated earlier than the Earth's moon, and this is just a function of time?
All of the above. The other thing is, right, so the Earth, in many ways, in lots of ways, is special, right? And the fact that Earth has oceans that are on the outside and that slosh around actually are one of the things that help keep us moving around. But certainly the size of Pluto and Charon relative to one another caused that. So initially we assumed that they were spinning independently, but ultimately over time those tidal forces slow them down until they get locked to face one another, right? So initially the moon too spun, but now it's tidally locked to the Earth. And it has to do with all of the things that you mentioned, the relative sizes, the closeness, the age at which the system was born, all of those things factor into how that spin down happens and they get locked up.
I actually have two questions. My first is, what would happen if Charon got too big and popped like a balloon? And due to Charon getting really big, do you think that it would ever squish Pluto or damage Pluto in any means?
Okay, so that's a good question. So the expansion that I talked about it like a balloon. but the amount that it got bigger wasn't very much. It was only a kilometer or two, but that's enough to cause this cracking. So it's unlikely that it would have gotten big enough to explode. You would need a lot of water to freeze, although that would be super cool to see happen. And it's not going to get, like I said, you need a lot of water. So it's not going to get big enough to get to Pluto, right? It's still 16 Pluto radii away. It'd have to be really big to affect Pluto in that way. And we don't think that would have happened.
Okay.
Did I answer both of your questions?
Yes.
Okay, awesome.
Yes, I have a comment and then a question. The comment is fascinating stuff from an uneducated, non-planetary scientist kind of guy, and you're incredible how you present that story.
Thank you.
And when you talked about the evidence that you put together from a forensic perspective, what would be the evidence that would say that it was not the story that you told, but instead a different story? For instance, again, uneducated eye looking at that picture, maybe it's material on the top half of the southern hemisphere that got removed that may have been liquid, which would have left a smooth surface, because it looks like, almost like you take the kind of the top chocolate shell off ice cream from the bottom section of it, and then it kind of looks like that top section's bigger. So what would the evidence be that would say that couldn't have happened?
Sure, so you're asking the wrong guy, because I got a story that I really like.
Okay.
But
Yeah.
you would have to create a story that is consistent, right? So if you had, right, so you're talking about like a shell that chipped away, right? So like, how would you do that? You have to come up with some mechanism to pop that shell off.
Water and ice or something else that just disappeared.
So you'd have to find some way to explain that, to find some mechanisms that do that. Maybe there's some other exotic chemistry that would do that. Maybe it was just formed that way to begin with, and maybe you had cracking in the north and not in the south. Maybe what we're seeing in the south is an original smooth surface, right? But you'd have to make that consistent with all the data. And I don't know how to do that, but I'm sure someone will, and write a new paper about why Charon is like it is. And that's science.
And do you think that mass on the southern hemisphere is actually different and slightly smaller in diameter than that northern hemisphere?
Yeah, so the thing is that there are a couple of things. So we're talking about this as the north and the south.
Yeah, like at a tilt.
Right?
Yeah.
But really, remember, the sun, this is weird, the sun is coming kind of from the North Pole. So really, the equator of Charon is right here. And this low spot is on the equator.
Oh.
Okay? And the South Pole is down here around the curve of the planet in darkness. And so you're right in that the average elevation of this area is less, but not by very much, by a kilometer or two, right? And so we think, based on complete guesswork, that perhaps it's not smooth all the way down to the South Pole, but there's really more of a band around the equator maybe that's smooth like this, or maybe it's just on this side, because we really can't see the backside very well. And so that's where getting more data would be great, but we just don't have it. Those are all great questions.
Very
and
cool.
There are great
Thanks.
ways to start a scientific investigation, is to ask those kinds of questions. Yeah?
Yeah, thanks for all the information and all the great energy. Yeah, I guess my question goes back to, you're talking about this cryovolcanism that happens with the water freezing and then the ammonia, the content getting higher. So that was in the past. Does the chemical composition of what we detected on Charon also confirm this, what's left over? And how long ago did that happen?
Oh, that's a great question. I see you're wearing a New Horizons shirt. Yeah. All right, so you might think this will sink me. So the problem you have raised is a great question. So you might assume, based on what I said, that those smooth plains should show an ammonia signature, right? If they're made of ammonia, water, lava, it should be ammonia on the south and just water on the north, right? It's all water. But I've got an answer for that, and that is ammonia gets, if it's on the surface of an icy body, we think that when, over time, sunlight, just the simple radiation from sunlight, causes ammonia to pop off of a surface and leave the water. And so my counter to that is that when the ammonia water flow flowed out, it was certainly rich in ammonia. But over time, right, and this is an old surface. This happened early in the solar system. Over time, that top layer has been, all the ammonia has popped off and escaped into space. And so the top layer of this lava flow, my prediction is that the top layer of this lava flow is ice, and that's what we see from the spectrometers. If we ever went down there with an excavator, you would dig through that crust, and you would see a top layer of mostly water ice, and down below you might see that mixture of ammonia water. But you need an excavator. So.
Hope you get to send one. Thank you.
Very good. Yeah.
This dovetails a bit on a previous question. I don't think you mentioned whether the Pluto-Charon orbit is nearly circular or has or had a pronounced eccentricity. If the latter, could that be a possible source of energy to drive some of the geologic processes through tidal stresses?
Sure. So early on, certainly the tidal motion, even though it was a lot less between Pluto and Charon than it would be between a giant planet and an object like Europa, some of that does pump tidal energy in early on. But just as objects, as a normal kind of evolution, objects tidally lock and face each other, their orbits often also tend to circularize, right? So it's possible that early in the system's history, the orbits were more elliptical, but now as we see them today, they are very, very nearly circular. And so it's kind of a low energy orbital state, right? Yeah?
It's a two-part question. Which side of the picture right here is Pluto tidally locked, like the north, south,
so
left or right? Like that?
Okay, so let me answer that. So the sub-Pluto point, like if you were standing and you were looking straight up, where would that point be? Right, so that would be on Charon's equator, right about here. Right, so this is the sub-Pluto hemisphere of Charon, right? Okay. I have to do this right, otherwise I'll get the sub-Charon spot on Pluto is on the backside of Pluto that we did not see as well. Okay. Yes?
Yeah, so I forgot to ask this question in the beginning, and it's kind of related to the semi-previous question that was asked. So what I wanted to know is that do Pluto and Charon have a elliptical orbit, kind of like the Halley's Comet does? And if
you mean around each other or around the sun?
Around the sun.
Okay.
And the second part is that if true, then is there a chance that Pluto and Charon would complete a rotation around the sun, or it would crash into another planet or a satellite belonging to that planet, and when?
Okay. So, of course, in reality, all orbits are ellipses. It's just that some ellipses are more circular than others. Pluto and Charon, the Pluto system orbits the sun in a reasonably elliptical orbit. It's not as elliptical as a comet orbit. It's still pretty circular, but there are some places, right? So you may have heard this. There are some places where when Pluto and Charon are closer to the sun than the distance of Neptune, and sometimes they're farther away. So it is a little more elliptical than other of the big planets in the solar system, but not by a lot. And it takes Pluto and Charon about 250 years to go all the way around the sun. So we haven't seen a complete rotation yet. Also, where they are, it's pretty empty. There's not a lot of stuff out there. So right now, the likelihood of them running into something else is pretty low. But clearly, things have run into them. You can see the craters on their surfaces.
Yeah.
Yeah.
Thanks, thanks for your time. I was wondering.
Thanks for coming.
Thanks. Since for some reason I was assuming whenever there is a chance for living on some planet, we study that planet, but you answered that's basically very cold and very far away. So I really like to know what's next. What's the future plans? Or discoveries.
For what? For NASA, for humanity, for New Horizons?
Yes.
Good, because that's one I can probably answer. So, so after we flew by through the Pluto system, we were, like I said, we're on this rail out of the solar system. We adjusted our orbit, our trajectory a little bit. We had a little bit of fuel to kind of bend the orbit. And so we flew by the KBO object MU69 this Christmas, this New Year's. And Andy said that Jeff Moore will talk about what we learned there, so I'll keep you in suspense. But now we're past MU69. It's far behind us now. We continue to move super fast. We hope in our wildest dreams, so the way that NASA funds things is it funds it in chunks. And what we're planning to do is to propose for another extended mission to try and use New Horizons as a telescope to find other Kuiper Belt objects that are in the area that we can kind of maybe get to. Because we're so far out now that even though the cameras on New Horizons were built as cameras to look at things that we were kind of close to, they're still better telescopes than telescopes that are 33 AU away on the Earth. So our plan is to try and use New Horizons as an observatory to find other Kuiper Belt objects that are in our path that we may have enough fuel to nudge our trajectory a little bit, and maybe we'll be able to fly by another one. And if not, we'll become an observatory in the Kuiper Belt looking at other Kuiper Belt objects. Thank you. Yeah?
Hi. You mentioned about the loss of ammonia from the surface due to either, is that evaporation or sublimation?
Sublimation.
Yeah. I was just wondering, what's the intensity of sunlight like out there? Is that image there enhanced? Can you give some idea of how bright it actually is out there?
So it's certainly very dim. There was a campaign, a public relations is probably not the right word, an educational campaign around the time that we flew by Pluto. I forget what it's called now. I'm going to get lambasted for not knowing what it's called. It might have been called Our Pluto. I'm not sure. But it was a campaign to kind of show you how bright it would be if you were on Pluto. And it turns out that it's a lot brighter than you kind of think. So there's a time at dusk. So there's a website, oh gosh, I wish I could remember it, that could say, you could say, I live here, and it would say, okay, you live here. Today at this time of night is the brightness it would be if you were standing on Pluto. Right? So there's a time at dusk, right? So it wasn't full darkness on the Earth. It was like a period at dusk where the light level would be about the same if you were on Pluto. So it's a little brighter even than I thought it was. So kind of almost dusk, almost dark conditions, if that helps any. And this is certainly brightened and enhanced so you can see it better.
All right, let's do one more.
One more question. You are the last question, sir.
Thank you for the presentation. It was really amazing. So I have two questions. One is, given that Pluto was the primary mission for New Horizons, why was the choice made just to do a flyby and not really, I don't know, like get into an orbit around it? And given that Pluto is no longer a planet, will there be, like, is there any justification for further missions to Pluto?
Okay, so those are great questions. The answer to the first question about why we didn't orbit Pluto, the answer is a combination of money and physics. So to get to Pluto in only 9 years, we had to be going fast, way fast, right? So New Horizons, like I said, is the size of a grand piano. It could easily fit on this stage. And we put it on top of the biggest rocket NASA could buy, an Atlas V, right? Which is basically, right, rockets, if you don't know, rockets have a small engine at the bottom, but the big silo is full of gas. It's a fuel tank, right? So that huge rocket got us going fast in the solar system, to cross the solar system to Pluto in only 9 years. For us to go into orbit around Pluto, we would have to bring a rocket's worth of fuel tanks to burn, to slow down, to get captured by Pluto gravitationally. And we just couldn't afford to launch that much fuel with the spacecraft. Or we could have chosen to go slower, right, and not go as fast so we wouldn't have to brake as much, but then all of the people that started the mission would be dead. And they would not like that. They really wanted to see Pluto before they died. So it's a combination of those factors. You mentioned what the prospects are for doing more exploration of Pluto. And whether you believe that Pluto is a planet or not, certainly the IAU, it's still a planet, right? A dwarf planet is still a planet, as we like to say. But it doesn't really matter what we call it. Pluto doesn't care what you call it. Scientists that study objects in the solar system, we don't really care what you call it. If we can, as scientists, make a good case for why it's important for the American people, or scientists in other countries can make that case of why it's important to send another spacecraft to learn more about Pluto and Charon, if we can make that case to the government and the American people, then a new mission will get funded. And so we think that the things that we have learned at the Pluto system are tantalizing. There's a whole half of the planet that we haven't seen, and another half that was in complete darkness. Of course, we kind of have to wait 125 years for the other side to get lit, so it's kind of a problem. But the data for Pluto and Charon, the Pluto system, are, as I said, they're tantalizing. And so trying to get another mission in the future, I think, has probably pretty good prospects. I think we could make a good science case for trying to go again and trying to figure out how we might be able to go into orbit instead of just screaming by. Thank you very much.
Thank you for ending our series this year in such a splendid way. Everyone, please drive carefully, and we'll see you in October.